Full explanation and more details of hybrid electrolytic capacitors. Hybrid electrolytic capacitors are a type of capacitor that combines features of both electrolytic and solid-state capacitors to achieve improved performance characteristics. Traditional electrolytic capacitors are known for their high capacitance values and relatively low cost, but they also have limitations such as high equivalent series resistance, ESR, limited reliability, and poor performance at high frequencies. To address these limitations, hybrid electrolytic capacitors incorporate elements of solid-state capacitors, such as conductive polymer materials or ceramic materials, into their design. This hybrid construction allows them to maintain high capacitance values while improving other key parameters such as ESR, reliability, and frequency response. Here are some key features and advantages of hybrid electrolytic capacitors. ESR stands for equivalent series resistance, which is the effective resistance that appears in series with the capacitance of a capacitor. In electrical circuits, any component, including capacitors, exhibits some level of resistance due to factors such as the internal structure of the component, material properties, and manufacturing processes. Low ESR in capacitors is desirable because it minimizes the voltage drop across the capacitor and reduces energy losses in the form of heat. When a capacitor with low ESR is used in a circuit, it can deliver more stable and efficient performance, especially in applications where fast switching or high-frequency signals are involved. In the context of hybrid electrolytic capacitors, achieving low ESR is a significant advantage. Traditional electrolytic capacitors, while offering high capacitance values, often have higher ESR compared to other types of capacitors. This higher ESR can lead to inefficiencies in circuits, increased heat generation, and limitations in handling high-frequency signals. Hybrid electrolytic capacitors address this issue by incorporating elements of solid-state capacitors, such as conductive polymer materials or ceramics, which inherently have lower ESR. By combining these materials with traditional electrolytic capacitor structures, hybrid capacitors are able to achieve lower ESR values while still maintaining high capacitance. The low ESR of hybrid electrolytic capacitors makes them particularly well-suited for applications where low impedance and efficient power delivery are critical, such as in power supplies, voltage regulator modules, filtering circuits, and decoupling circuits. Additionally, low ESR capacitors help improve the stability, reliability, and performance of electronic devices across a wide range of operating conditions. High ripple current handling. Ripple current is the fluctuating current that flows through a capacitor in applications where the voltage across the capacitor is not constant. It often occurs in power supply circuits, where the capacitor filters out the AC component of the voltage, leaving a DC voltage with small ripples. Hybrid electrolytic capacitors are designed to handle high ripple currents effectively. The lower equivalent series resistance, ESR, of these capacitors helps in reducing power losses and heat generation, making them capable of handling higher ripple currents without significant temperature rise or degradation in performance. Capacitors with high ripple current handling capability are essential for maintaining stable output voltages in power supply applications, where fluctuations in ripple current can lead to voltage droops and affect the performance of sensitive electronic components. Longer lifespan. The lifespan of a capacitor is determined by various factors such as operating conditions, temperature, voltage stress, and the type of materials used in its construction. Traditional electrolytic capacitors often have limited lifespans due to factors such as electrolyte evaporation, chemical degradation, and internal heating. Hybrid electrolytic capacitors typically have longer lifespans compared to traditional electrolytic capacitors. This is due to several factors. Improved materials. Hybrid capacitors incorporate solid-state materials, such as conductive polymers or ceramics, which offer better stability and reliability compared to the electrolyte used in traditional capacitors. Enhanced construction techniques. The construction techniques used in hybrid capacitors help in reducing internal stresses and improving the overall robustness of the capacitor, leading to a longer lifespan. Lower operating temperatures. The lower equivalent series resistance, ESR, of hybrid capacitors results in reduced power losses and heat generation, leading to lower operating temperatures and less stress on internal components, thereby contributing to a longer lifespan. Overall, the longer lifespan of hybrid electrolytic capacitors makes them suitable for use in applications where reliability and longevity are essential, such as automotive electronics, industrial equipment, and critical electronic systems. In summary, hybrid electrolytic capacitors offer advantages such as high ripple current handling capability and longer lifespan, making them well-suited for a wide range of applications where reliability, efficiency, and performance are crucial. The longer lifespan of hybrid electrolytic capacitors compared to traditional electrolytic capacitors can be attributed to several factors. Improved materials. Hybrid electrolytic capacitors often incorporate solid-state materials, such as conductive polymers or ceramics, into their construction. These materials offer better stability and reliability compared to the electrolyte used in traditional electrolytic capacitors. Solid-state materials are less prone to evaporation and chemical degradation over time, resulting in a longer lifespan for the capacitor. Enhanced construction techniques. Hybrid electrolytic capacitors may utilize advanced construction techniques that help reduce internal stresses and improve the overall robustness of the capacitor. These techniques include optimized electrode designs, improved sealing methods, and better encapsulation materials. By minimizing stress points and improving structural integrity, hybrid capacitors are better equipped to withstand environmental factors and operating conditions, thus extending their lifespan. Lower operating temperatures. The lower equivalent series resistance, ESR, of hybrid electrolytic capacitors results in reduced power losses and heat generation during operation. Lower operating temperatures contribute to the longevity of electronic components by reducing thermal stress and preventing accelerated aging. Hybrid capacitors, with their lower ESR, are capable of operating more efficiently and reliably over extended periods, thereby increasing their lifespan. Improved reliability standards. Manufacturers of hybrid electrolytic capacitors often adhere to stringent quality control measures and reliability standards during the production process. This includes rigorous testing procedures to ensure consistent performance and durability under various environmental and operating conditions. By meeting or exceeding industry reliability standards, hybrid capacitors demonstrate a higher level of reliability and longevity compared to traditional electrolytic capacitors. Overall, the combination of improved materials, enhanced construction techniques, lower operating temperatures, and adherence to reliability standards contributes to the longer lifespan of hybrid electrolytic capacitors. These capacitors are designed to provide reliable performance over an extended period, making them suitable for a wide range of applications where longevity and durability are essential considerations. Improved frequency response. Improved frequency response in hybrid electrolytic capacitors is achieved through several design features and materials used in their construction. Here's how. Solid-state components. Hybrid electrolytic capacitors incorporate elements of solid-state capacitors, such as conductive polymer materials or ceramics, into their design. Solid-state materials have inherently faster response times compared to traditional electrolytic materials. This allows hybrid capacitors to respond more quickly to changes in voltage or current, resulting in improved frequency response. Lower equivalent series resistance, ESR. The use of solid-state materials in hybrid capacitors helps reduce the equivalent series resistance, ESR, compared to traditional electrolytic capacitors. Lower ESR allows hybrid capacitors to maintain their capacitance values more effectively at higher frequencies. This is crucial in applications where rapid changes in voltage or current occur, such as in switching power supplies or high-frequency filtering circuits. Improved dielectric properties. The solid-state materials used in hybrid electrolytic capacitors often have superior dielectric properties compared to traditional electrolytes. This results in reduced losses and improved signal integrity at high frequencies. Capacitors with improved dielectric properties can effectively filter out unwanted noise and interference, making them suitable for applications requiring precise signal processing. Advanced construction techniques. Hybrid electrolytic capacitors may utilize advanced construction techniques, such as precision manufacturing processes and optimized electrode designs, to enhance their frequency response. These techniques minimize parasitic effects and improve the overall performance of the capacitor across a wide range of frequencies. Stability over temperature. Hybrid capacitors are designed to maintain their electrical properties, including capacitance and ESR, over a wide temperature range. This stability ensures consistent performance of the capacitor across varying operating conditions, including temperature fluctuations, which is essential for applications requiring reliable frequency response. Overall, Hybrid electrolytic capacitors offer improved frequency response compared to traditional electrolytic capacitors, making them suitable for applications where fast response times and precise signal processing are necessary, such as in power supplies, audio equipment, telecommunications, and high-frequency filtering circuits. Compact size is an important characteristic of hybrid electrolytic capacitors, and it is achieved through several design innovations and material choices. High capacitance density. Hybrid electrolytic capacitors are designed to achieve high capacitance values in a compact form factor. This is achieved by utilizing advanced materials and construction techniques that maximize the capacitance density within the available space. Solid-state materials, such as conductive polymers or ceramics, often have higher dielectric constants compared to traditional electrolytes, allowing for higher capacitance values in smaller volumes. Optimized electrode design. Hybrid capacitors may feature optimized electrode designs that allow for efficient use of space while maintaining high capacitance. This includes innovative electrode configurations, such as folded or stacked electrode structures, that maximize the electrode surface area within the capacitor's dimensions. Miniaturization technologies. Manufacturers of hybrid electrolytic capacitors employ advanced miniaturization technologies to reduce the physical size of the capacitor while maintaining or even increasing its capacitance. This includes precision manufacturing processes, such as laser drilling and microfabrication techniques, that allow for the production of smaller and more compact capacitor components. Thin-film dielectrics. Some hybrid electrolytic capacitors utilize thin-film dielectric materials, which offer high capacitance density in a thin and lightweight package. Thin-film dielectrics can be deposited on a variety of substrates, enabling the production of compact capacitors with high capacitance values for use in space-constrained applications. Surface mount technology. SMT hybrid electrolytic capacitors are often designed for surface mount technology, SMT, which allows them to be directly mounted onto printed circuit boards, PCBs, without the need for additional lead wires or through-hole mounting. SMT-compatible capacitors have smaller footprints and lower profiles compared to through-hole capacitors, making them ideal for compact electronic devices and densely populated PCBs. Overall, the compact size of hybrid electrolytic capacitors makes them well-suited for applications where space is limited, such as in portable electronic devices, automotive electronics, and miniaturized electronic systems. Their high capacitance density and small form factor allow for efficient utilization of space on PCBs while providing the necessary energy storage and filtering capabilities. Wide operating temperature range. Compact size. Hybrid electrolytic capacitors are often designed to be more compact compared to traditional electrolytic capacitors while still offering high capacitance values. This is achieved through advancements in materials and construction techniques. Advanced materials. Hybrid capacitors may incorporate solid-state materials such as conductive polymers or ceramics, which can achieve higher capacitance densities compared to traditional electrolytic materials. This allows for higher capacitance values in smaller package sizes. Enhanced construction techniques. Manufacturers utilize advanced construction techniques to optimize the internal structure of hybrid capacitors, reducing the overall size while maintaining high capacitance. This includes precision manufacturing processes and innovative electrode designs. The compact size of hybrid electrolytic capacitors makes them ideal for applications where space is limited, such as in compact electronic devices, mobile devices, automotive electronics, and other miniaturized systems. Wide operating temperature range. Hybrid electrolytic capacitors are designed to operate reliably over a wide temperature range, making them suitable for use in demanding environments and applications where temperature variations are common. Several factors contribute to the wide operating temperature range of hybrid capacitors. Advanced materials. Solid-state materials used in hybrid capacitors offer improved temperature stability compared to traditional electrolyte materials. These materials can maintain their electrical properties over a broader temperature range, ensuring consistent performance. Robust construction. Hybrid capacitors are constructed using materials and techniques that enhance their durability and reliability in harsh environments. This includes robust encapsulation materials and optimized electrode designs that withstand temperature extremes without compromising performance. Thermal management. Hybrid capacitors may incorporate features to improve thermal dissipation, such as low ESR designs that minimize heat generation during operation. This helps maintain stable performance even at high temperatures. The wide operating temperature range of hybrid electrolytic capacitors makes them suitable for use in automotive electronics, industrial equipment, aerospace applications, and other environments where temperature fluctuations are common and reliability is crucial. Overall, compact size and wide operating temperature range are important characteristics of hybrid electrolytic capacitors, making them versatile components suitable for various electronic applications in demanding environments.